can tell, this thing is a beast. It's a 7-liter LS, 650-ish horsepower, 6-speed manual Tremec transmission. It's got headers on it, Cook's headers. It's got an Atlas 2, heavy-duty axles. Got a lot of stuff. Got a Gen Right fuel tank because we couldn't run the headers on a 2-door. Without moving the fuel tank. This engine was built by Colby over at Ellis Turnkey. It's a 7-liter 427 engine, which is kind of ironic because that was the iconic small block Chevy of the late 1960s. It drives really nice on the highway. 6th gear is good above 80 miles an hour at about 1900 RPM. It doesn't really like to run much lower RPM than that because the cam has to get in its power band. Surprisingly, it's running cool. You can see our AC condenser here and no transmission cooler. Obviously, it's a manual transmission. Hope you guys can hear me. This morning we're in a 2011 JK with a 7-liter LS manual transmission, 6-speed. Yeah, we got a Tremec 6-speed in this one. It's a beautiful transmission. It really shifts nice. Gear spacing is good. The space between 5th and 6th is a little bit stretched, but when you get up to about 80 miles an hour, 6th gear is really nice. I'm going to do most of this video on the highway for obvious reasons. This is a 7-liter engine that was built by LS Turnkey. It has a Tremec 6060 4-wheel drive transmission by George over there at Tranzilla, or what is it called, Rockland Gear. Just a great shifting transmission. This Jeep is a perfect example of 10 pounds in a 5-pound bag. It's got Cook's headers on it, which really are not designed for the 2-door JK. Yes, this is a 2-door because the passenger side header just dumps right out into the fuel tank. So of course the fuel tank had to be relocated. We got a Gen Right tank in the back. Then we have an Atlas 2. So there's a lot of stuff in this little Jeep. One concern we have with 2-door Jeeps and long powertrains is drive shaft angularity and vibration. Fortunately, this has none of it, and I've come to realize over the years it's more of a art than a science. I've had Jeeps with less lift than this that vibrate, and I've had Jeeps with more lift than this not vibrate. This Jeep is making power the old-fashioned way, which is completely the opposite of, let's say, the LT1. Now this Jeep is rated at 650 horsepower or something like that, and you know it. When you start it, it's all rumpity-rump. With the fuel injection, it's not too bad as far as the smells and all that goes. It runs pretty clean, but it's idling at close to 1,000 RPM, and people can hear it across a parking lot. It brings back my days out of high school with 454s and 428s and cammed everything, because that's all we had. We didn't really have the sophistication of fuel injection and direct injection and all that. I remember driving through parking structures in Brentwood and Beverly Hills with like my Cam 396 Camaro and setting off alarms. Those were the days. The reality is you don't need to do that anymore. In today's world, you can have 600 horsepower with virtually the same drivability as any other engine. If you go to a supercharged engine, obviously that's not hard at all. In order to understand how we can make so much horsepower today with good drivability, we have to look back at what we were doing 30, 40 years ago. A lot of the potential energy of an engine is in the amount of cylinder pressure it can create. In addition to that, how much fuel and air can you get into it? The more fuel air charge you can get into it, obviously the more power you're going to pull out. Now kind of the king of the whole cylinder pressure piston thing has to be the steam engine. I'm not talking about turbines. Steam turbines are really efficient and they're still used today. Whether it's nuclear powered or boiler fed or whatever, just any kind of a heat source can power a steam engine. I was just thinking to myself how really there's nothing new under the sun. Way back when the Greeks were a powerful empire, and that's thousands of years ago, they actually had a steam engine. It wasn't a piston engine. It was basically a ball with a couple of ports, and if they boiled water inside of the sphere, it would shoot jets of steam out of the ports and cause the ball to turn. That's really a steam engine. And if you think about it, the Industrial Revolution could have happened many centuries previous. In addition, I remember seeing a painting of the Christ child holding a small toy that allegedly was popular back then. And what it was a stick with a couple of blades on top, just like the toys you can buy today at the drugstore. And you put it between your hands and spin it, and it flies up in the air. It's a propeller. So think about it. They had the propeller, aka helicopter, and steam engine thousands of years ago. So what we're doing here is really not that much different than what's been done for hundreds of years. If we look at a simple steam engine, just let's say a single piston steam engine, you boil water in a container, build up pressure, and feed that into the steam engine on top of the piston. Pushes the piston down, causes a crankshaft to rotate. There you go, you got a steam engine. Now, the previous steam engines were beam engines. They really didn't have the crankshaft early on in the 1700s. It was developed quickly, though, because a rotating crankshaft was a lot easier to get power from than a beam engine going up and down. Now, the beam engine would turn a shaft that would, of course, turn a crank, but eventually everything moved into a rotating crankshaft. So they knew back then, the more pressure you put on top of that piston, the more power they're going to get out of the engine. They had valve timing for these, whether it was a slide valve or a rotary valve, but they basically had to feed the steam in at the right time and shut it off at the right time. Then they had exhaust. They had to exhaust it at the right time, just like a modern engine. Well, some smart guy said, hey, if we can push steam on top of the piston, why not push it on bottom of the piston? And they did. So now you had a steam engine with a piston that was like a pancake, and you could feed steam pressure to the top of it. Then when it got to the bottom of the stroke, to the bottom of it, we'll push it back up. And because these engines put power out in every stroke, a simple single piston steam engine was more like a four-cylinder, four-stroke engine of today, because you're putting power out in every stroke, and you're putting power out when the piston travels up and when the piston travels down. So of course the technology evolved, and guys got all into the valve timing, and one of the things they had to do was limit the speed of these steam engines because they could run away, and they were big heavy moving parts that really weren't designed to go fast. So they had these balls that would fling out as they were basically centrifugal governors. So as the steam engine would spin up, the balls would swing out and close a valve, the steam supply valve, which would then slow the engine down. It was a regulator, and that term you've heard, balls to the wall, that's where it comes from. Steam engines evolved over the centuries, and they had compound, complex, multi-cylinder engines where you would have a high-pressure piston that was small in diameter. Then behind that, you'd have a medium-sized piston for the steam that came out of the high-pressure piston. Then behind that, you would have a low-pressure piston, which was larger, because the larger the diameter of the piston, the more effect the pressure would have, and since the pressure was lower, you wanted a larger surface to work against. And then they learned how to recirculate the steam into a condenser so that you could put the water back into the boiler so that you didn't have to constantly add water to your steam engine. They figured out what super steam was, which increased the pressure dramatically. And some of these engines could run 800-900 degrees. Modern pistons and rings probably could not hold up to some of the technology these steam engines had. And steam powered the earth for centuries, whether it was locomotives, factories, eventually cars. Steam engine cars are one of the most popular forms of transport back in the turn of the century. That is the last century, in the early 1900s. Even the president used a steam car in the first decade of the last century. But let's move on. The ICE engine, or the internal combustion engine, came around. Steam engines are known as external combustion because you're building the pressure up in an external cylinder or container. And that's where, let's say, a nuclear-powered submarine with a steam turbine can be so efficient, because nuclear power can create a lot of heat, and then you feed that into a turbine or piston engine or whatever, and it's extremely efficient. So many of the luxury liners from the heyday of luxury liners were steam turbine powered. I bet you a lot of you didn't know that the Titanic had a steam turbine on board. Now, of course, it wasn't nuclear powered, it was coal or oil, whatever they used for fuel, but it was a steam turbine on one of its engines. So the internal combustion engine takes the fuel and it injects it right into the cylinder. And there's a lot of advantages to that. These engines are a lot smaller, a lot more compact, especially for mobile vehicles. There was a steam-powered airplane, and imagine trying to package a boiler, a burner, the engine, the condenser. With an ICE engine, really all you had to do was shoot gasoline into a cylinder, and you had an engine. The principles of intake and exhaust were very similar. Valve timing was very important, and there was a lot of different ways tried. There were sleeve valves, there were rotary valves, but as we all know, the good old stick valve became the most prominent. Now, was it the most efficient? No. Sleeve valves were probably more efficient. But the regular old valve was just so efficient and so easy to produce that that's where the industry went. Now, the first engines were mostly flathead. These were engines that had evolved out of the age of steam. They were low pressure or no pressure oiling systems. So you couldn't really put a whole lot of stress on these engines. The valve was upside down compared to what you're used to today. The stem pointed downward. And that way the camshaft was internal and pushed the valve up. So you had a flat cylinder head. You can just literally make a flat cylinder head, bolt it on there, and you had an engine. They were simple, they were reliable. The Ford flathead V8 and the other flathead engines, 4-cylinder, 6-cylinder, inline, whatever, powered this country for many decades. Now these engines, like I said, they had low pressure oiling systems, very low compression, which a lot of was due to the fuel available at the time and the oil available at the time and the metallurgy available at the time. So some of these engines are running 4-to-1, 5-to-1 compression. When manufacturers were hitting 7, 8, 9-to-1, those were considered really high compression engines. And that really came about in automobiles in the late 1940s and early 1950s. And if you look at the temporal effect of that, it was mainly because of the war effort. World War I, we pretty much had most of the piston engine technology we were ever going to get. Now, yeah, we didn't have the computers and such. We had overhead cams. We had dual overhead cams. We had 4 valves per cylinder. We had all this technology, but what was limiting it was the metallurgy, the fuels, and the oil. Now, of course, the means of production also. We didn't have thin wall castings and core casting technology that they eventually developed with CNC machines and numerically controlled machines and all of that. But they were still able to crank out lots of these engines. Louis Chevrolet built a dual overhead cam 4-valve cylinder for the Ford Model T, and he raced it, and he won. Chevrolet became a big name. Now, unfortunately, he didn't do a whole lot with that name. General Motors, I believe it was William Durant, got a hold of that name and used it because of Louis Chevrolet's fame. But Chevrolet actually went on to work for AMC, American Motors, and never really got the fame that he deserved. But the metallurgy was where it was at. They could crank these engines up. They had radial engines and rotary. Rotary is where the cylinders turn and the crankshaft stays stationary. Radial is where the crankshaft turns and the engine stays stationary. But they had some really high performance engines, and they were melting exhaust valves. They were melting pistons. They just didn't have the metallurgy. Well, that time between the war, 20s and 30s, there was a lot of developments in ICE technology. What the British, Americans, and Italians and Germans did was pretty amazing. They built engines that were thousands of horsepower. The first engines were really limited in their duration and their duty cycle because they were so high stressed. The Schneider Cup was an event to display these improvements in technology. And while these engines put out thousands of horsepower, they really couldn't go the distance. They couldn't fly, let's say, in an airplane for thousands and thousands of miles, as would be required in war. They were only short duration engines. So they worked really hard on getting these engines more and more reliable. These engines had war emergency power. They used water injection, methane injection, all sorts of technologies to get more and more horsepower. And eventually, they exceeded the 1 horsepower per cubic inch. Really crazy designs came out. Now, of course, they had big camshafts, and we'll talk about that. They had superchargers, turbochargers, super turbochargers, sleeve valve, just anything that their minds could imagine. When it became apparent there was going to be a Second World War, not only were they looking for horsepower, but they were looking for longevity and economy. What does that tell you? It's just where we're at today. They wanted the power, obviously, to outperform their foe. They wanted the longevity so that these engines could go the distance. In an airplane, the flight combat radius is very important. And one of the things that contributed to winning World War II was the P-51. The 109 was a great fighter. The Spitfire was a great fighter. But like Churchill said, the P-51 could do what the Spitfire could do, but 500 miles further out. When Goering saw P-51s over Berlin, he knew the war was over. So getting these engines to get the economy and the power was key. The most efficient combustion chambers were designed. Overhead cams, multiple valves, high compression. And one of the big contributing factors, again, fuel. By World War II, the Americans' fuel with a high octane, 150 plus octane, really made American fighters and British fighters outperform the rest. By having this high octane fuel, they could crank the boost up, the cylinder pressure up, and have anti-knock tendencies. So for any given size engine, we would outperform our adversaries. Another was lubrication. Lubrication came a long way. Synthetics were coming around. Really important was the metallurgy, because while they were getting more power and leaning these motors out for economy, the engines were running hotter and hotter. And that really was kind of the restricting factor in a lot of engines, especially at altitude, was how hot they could run. And then we had guys like Charles Lindbergh, who concentrated on how to best get range out of any given engine. Lindbergh went to the South Pacific and trained Marines and others how to go long distances over water with a given amount of fuel supply. The right altitude, the right manifold pressure, the right mixture settings. You don't want to hurt your engine, but at the same time, you want to get that maximum flight range. So all this happened around World War II, and you say, well, they didn't have the computers we have, and they didn't, but they kind of did. They did have computers. The Germans had computers in some of their fighters, like the Focke-Wulfs, that would do automatic spark timing and fuel control. They had fuel injection. They had super lubricants. One of the things the Germans didn't have until the end of the war were high octane fuels. And that's why a lot of their engines, even though they were V12s and they were 30 plus liters, they couldn't produce the power that our 27-liter Merlins and other Allied engines were putting out, because we had that high octane fuel. So it just made sense after World War II, this internal combustion engine phenomenon would explode, and it did. That's when the hot rodders came around. You talk about a little deuce coupe. I actually worked on one with a Corvair engine, but the mainstream manufacturers knew that performance would sell. So by the mid-50s, all the major manufacturers were coming out with V8 engines. Obviously Chevy, the small block, and Ford had the Y motor, and Chrysler, everybody had a V8 engine. The Chevy small block was really ahead of the rest in its casting technology. They used thin wall castings, which made the engine lighter, and they reduced the number of castings to a minimum. I forgot, 20-something cores. And what you had is an engine that they could build in mass production and make money on. Remember, the V8 engines were nothing new. They were around since before the teens, but they were extremely expensive engines, almost handmade. Tolerances were tight, they were heavy, they were large. The new small block Chevy in 1955 did a lot of things, and it used technology from the war. The oiling system in the small block Chevy wasn't revolutionary, but they applied technology that they learned during the war about where these ports should be on the crankshaft and how to lube the camshaft after the crankshaft, because of prioritizing what needs oil more importantly. And of course we went to high pressure oiling systems so that the wear was brought down to almost nothing. Most of the wear in your engine is during startup. Of course we had the lubricants now, and of course we had the better fuel. So what that meant is we could crank the compression up 8-to-1, 9-to-1 engines came around, and by the 60s 10-to-1, 11-to-1 engines were coming around, and that persisted right up through about 1970. In 1970 things were getting out of control. We basically had chassis that hadn't evolved that much. We were putting 500 horsepower engines in them with single master braking systems and torsion bar suspension that was really floppy, and things were just getting dangerous. So the Fed stepped in and started to cut back on horsepower, compression. The insurance companies were starting to jack the rates up on high performance engines. But let's not talk about that. So in the 60s, which is really one of my favorite decades, we didn't have all the restrictions. Early 60s, we didn't even have the emission constraints that we had in the late 1960s. So engineers and designers were able to do whatever they wanted. And what they knew was they could take advantage of these new lubricants. They could take advantage of these new high-octane fuels. They could crank that compression up, get that cylinder pressure up, and cram as much fuel into the chamber as they could get. And that was the start of the manufactured horsepower race. Now call it whatever you want, a 413 wedge or a 409 Chevy. They were experimenting. They were trying to get whatever they could out of these engines. And one of the things was a camshaft. Why is the camshaft so important? Well, you can raise the compression on an engine, but everything had to work together. Remember, to get the air into the engine, you got to get the air out of the engine. I remember seeing guys take 800 double pumpers, putting them on their little 305 Chevy engines, and they were actually slower. Why? The exhaust was so restrictive, the cam was so small, nothing worked together. In order to make these engines work, everything had to be tuned to each other. So you had to have free-flowing intake that matched free-flowing exhaust. And you had to have a camshaft that would get that fuel air charge into the engine. Well, the early camshafts were very mild. And by the 1970s, the smock camshafts came around. Smock camshafts were designed to get better economy and lower emissions. But without getting into too much detail, basically a camshaft's job is to get as much air into an engine as it can if you're looking for performance. So what that meant is we had to keep that intake valve open as long as we could to get as much air in as possible. Then we had to open the exhaust valve as long as we needed to get rid of all that charge and scavenge the new air fuel charge into the engine. Well, what they found out was air is elastic. It can be rubbery. So by revving the motor up and getting a column of air that's moving very fast, you could literally keep the intake valve open after the piston reached bottom dead center. They realized that air was elastic. It's not a solid. It's affected by pressure, temperature, humidity, and other variables. But what they knew was in order to get the maximum amount of fuel into the chamber, they needed enough air or oxygen to burn it off. And that's where nitrous oxide comes in. But we're not going to talk about that. That's a whole different thing. Not many guys run on the bottle anymore. So how do you get more air into the engine? Well, an internal combustion engine is really not that much more than an air pump. So obviously running it faster meant more air was flowing. And if you got that air moving fast and you had a column of air that was elastic, you could cram it into a cylinder even when the piston was moving back up. And I'll try to explain. Most camshafts would shut the intake valve when the piston hit bottom dead center. Because obviously if the piston's at bottom dead center, it's sucked as much air in as it can get. Once it starts going up, it's going to start pushing that air back out into the intake. And that's where you get that rumpity rump. They knew if they had a column of air moving really, really fast in an intake, or better yet, a long runner, or a tuned runner, or better yet, a ram runner. You remember the old ram stacks that they used to run in the late 50s, 60s? Essentially what happened is this air is moving so fast because the engine is moving so fast. After that piston comes down to bottom dead center, the air is still cramming into the cylinder. So they leave the intake valve open. Right when that column of air stalls, they want to close the valve. Now that's going to be a higher RPM. That's going to be 3,000, 4,000 RPM. And the Can-Am engines and the muscle car engines, that's what they all did. They revved the motors up. They had big camshafts that closed the intake valve after bottom dead center. They got that air in there. Then of course they got the fuel into there. They went to bigger carburetors, 780s, 800s, double pumpers. And that was great. We were putting out 400, 500 horsepower, just like we are today. But the drivability sucked. Now this engine, while rumpity rump and loud and some would say annoying, may be music to somebody else's ears. I actually like the sound, but I also enjoy the drivability of the new engines. This engine having fuel injection makes it far easier to tune, makes a much better idle. There's just no comparison having this fuel control with a map sensor and a mass airflow sensor and all that. They're much more refined. The early cammed engines with carburetors, you got to remember, carburetors had Venturis based on the Bernoulli theorem, and they had to mix the air and the fuel together and then inject that through the intake manifold and distribute it to the cylinders equally, or as equally as they could do it. And at low RPM, when you've got pulses of air coming back into the intake because the intake valve is now open after bottom dead center, at low RPM and idle, that piston is pushing that air charge back into the intake, disturbing the natural flow. So now you get that rump, rump, rump. but that's what you got to deal with to get the power at the higher RPM. The fuel injection does make that better. But if you're on a racetrack, you're at Le Mans, you're going 180 miles an hour, you don't really care about drivability. All you care about is power. If you're in an airplane and you're flying 300 miles an hour, escorting bomber, you don't really care about idling that engine for a small percentage of the mission time, because you're going to be in the air for hours upon hours. Therefore, the camshaft worked. Well, by the 1970s, emissions started to come around, and as you can imagine, having this intake valve closed after bottom dead center was terrible for emissions. Now we have raw hydrocarbons being blown out the exhaust because raw hydrocarbons are being blown right back up into the intake. And then we have carbon monoxide. We're not going to talk about NOx too much because the NOx is really created by the smog engines. But as far as emissions go, these camshafts were a mess. I was an emissions inspector, and I remember doing a Hemi. Guy put a big cam in a Hemi Cuda, and I wasn't trying to get it to pass, I was just trying to smog it. And he was blowing 3,000 hydrocarbons, that's parts per million, at idle. That's the best I could get it. That cam was so big. And the problem is you couldn't idle over 1,200 RPM because that was the state limit. So even at 1,200 RPM blowing 3,000 hydrocarbons, that vehicle wasn't going to pass smog. So now fast forward, the government comes down on the manufacturer. Hey, these engines are too powerful, the chassis. These engines are really dirty. So by the early 1970s, they started to crack down. The Air Resource Board came out about 1967, and emissions immediately started to get fit to California vehicles. Now, the positive crankcase ventilation system was a big improvement. PCV is still with us today, and it dramatically removed the emissions out of these engines. But the big camshaft thing had to be dealt with. And in 1970, between the insurance companies and the government, they really toned these engines down. The 1970 LT1, I think, is rated at 360 horsepower, and the 1970 LT1 at 330. And it just went downhill from there. They started dropping the compression ratios to run in the lower grade fuels. They made the cams smaller and smaller to meet emissions requirements. And the dark days of the 70s were upon us. The 8-to-1 305 small blocks were out there. The Midlands, the Windsors, the Chrysler 318. Now they all performed okay, but they were nothing like the fire-breathing ICE engines of the 1960s. So that's where I came in, and we had to take these engines from the 70s and 80s and make them perform. By the 1990s, though, I think technology kind of took over hot rodding. By the 1990s, going to fuel injection, we saw compression ratios rise. With computer control now, we can put engines in the closed loop, run at stoichiometric, which smart guys said is the optimal air-fuel ratio. It's about 14.7 to 1 on gasoline. That's the least amount of emissions with the best performance. So computers could hold stoichiometric. They tried doing it with carburetors. They had feedback carburetor, but that was just a short time span in the 80s and kind of a failure, in my opinion, because they were not very reliable. But by the late 1980s, pretty much everything went to a feedback or a closed loop feedback fuel injection system. So it used a sensor in the exhaust to measure air-fuel ratio, or an oxygen sensor. A narrowband oxygen sensor, which became the standard, measured stoichiometric. Computers targeted stoichiometric using fuel injection or some type of controllable fuel supply. Like I said, they did have feedback carburetors. Some operating systems had airflow meters. If you look at Datsun and BMW, they used a mechanical flow air meter, a vane type. Or if you look at Porsche, Bosch, they use that weird round circular vane. Other manufacturers like GM went to electronic airflow sensors. The early MAF sensors were awesome but troublesome. Some didn't use airflow meters at all, like Chrysler. They used speed density. It was a time for experimentation, and by the mid-1990s, engines had really cleaned up. Engines were now being designed from the ground up for emissions and performance. Cylinder head design had changed dramatically. The strength of the engines had changed dramatically. If we take a small block and compare it to an LS, which came out in the late 1990s, the LS, even the 5.7 LS1, had higher compression. It had a cross-bolted 6-bolt main. It had a skirted block. It had much more efficient cylinder head design. They did not go to a Hemi. They didn't think it was necessary. But the bottom line is we had an all-aluminum, lightweight, high-compression, high-output engine compared to what we had before. And because this engine was designed for emissions, the emissions control devices were minimal compared to the old days. If you look at a small block from the early 80s, late 70s, they had everything. They had exhaust gas circulation systems. Remember the old smog trees? They had air pumps. They had secondary air systems. They, of course, had evap systems, which doesn't do a whole lot of harm, but they just had a lot of stuff. Some of the LSs did run an EGR valve at the beginning of the Gen 3s, but by the Gen 4 and 5, they were mostly eliminated. Chrysler's still running an EGR valve. They're also running speed density, which, you know, it works, but in my opinion, and I think they do have an argument that the speed density system is simpler and less likely for failure. The flip side to that is when you have a airflow system working properly and you have accurate airflow tables for altitude and humidity and density, there's nothing else like them. When they're running right, they are the best for economy, performance, and everything else. But if you're at the track beating the crap out of your vehicle, racing it, speed density is probably a better option. So by the 90s, with this computer technology, everything wasn't port injected. You know, GM started off with their throttle bodies, and the 305 and 350 throttle bodies were great engines. I thought the K motor was one of the best small blocks ever made. They were reliable, they were durable, and one of the big things for us off-roaders is once they went to fuel injection, all that garbage with the carburetors on steep hills went away. So cold starts were no longer a problem with big camshafts, and going up steep hills or going down steep hills, we saw a lot less flooding of the carburetor or starving of the carburetor. I remember taking the Hollies and putting the side pivot floats on them and spring-loaded needle and seats and the Carters. They'd sell you the special off-road components for their carburetors. The throttle bodies worked pretty good. They were a big improvement over the carburetor, especially for cold start and environmental conditions like off-roading. But the writing was on the wall. They were popular in the late 80s and early 90s, but by the mid-90s, the feds were going to require misfire detection and cylinder shutdown. What that means is if you had a cylinder, let's say a spark plug went bad or you broke a valve spring, whatever, they wanted to be able to shut the fuel off to that cylinder to minimize emissions. So right around that time frame, GM did go to port fuel injection in some engines. And in my opinion, some of the best running small blocks were the tune ports. They weren't the easiest to service, but boy, they ran good. There was also the LT1, the early LT1, which had the opto spark. I was not a fan of that, but they were the next step from the throttle body to real port injection. Well, port injection had to be updated to sequential fuel injection to meet the Fed standards for onboard diagnostics too, which was cylinder, misfire detection, and shutdown. So we started to see some goofy stuff on the small block. They put a top dead center sensor inside of the distributor. Ford eventually got rid of the distributor and put that synchronizer, they called it, in. But essentially what it was a way to identify which cylinder was misfiring so that they could shut it down. Now, sequential fuel injection is a good thing because now the computer has control of each individual injector. Having control of each individual cylinder's fuel and then each individual cylinder's spark timing means you have almost full control of each cylinder, almost like 8 individual cylinders. Now, of course, it's not. They are connected by a common crankshaft, but it was much better than we had in the old days. So what this meant was differences in cylinders, and they could be up to 5, 10, even 15% due to inefficiencies, intake runner design, exhaust, etc. These new modern sequential fuel injection computers could deal with and get better economy, lower emissions, and better power because each individual cylinder could be controlled independently. So pretty much from the mid-90s up is the new era of engine performance. Everybody thinks it was a bad thing, but OBD2 was not a bad thing in my opinion. OBD2 standardized emissions. In the early days, we had connectors for every kind of vehicle, Ford, Chrysler, Chevy, Honda, Toyota, and it was a nightmare for a mechanic. When the federal government standardized the protocol and the data link connector, it made it a lot easier for us. In the mid-90s, the manufacturers got the idea, hey, we're kind of over meeting the emission standards and the economy standards keep getting tighter. We can really boost these engines. Let's increase the compression like we did in the old days. And then we'll find technology to allow that cylinder pressure and that high compression. So what came around? Direct injection, variable valve timing, continuous variable valve timing, cam phasing, multiple displacement technology where you can drop cylinders variable oil pressure. There's just so many different technologies that started to emerge and get put into production engines. They were getting more and more efficient. But the good thing is, we really weren't losing any horsepower. In fact, they were gaining horsepower. Chevrolet proved in the early 90s with the ZR1 Corvette, dual cam, 4-valve. They could put a tremendous amount of horsepower out and still meet all the regulations. Well, that motor was really complex, really expensive, really hard to service, so they dropped it. But what their goal was with the LS was to take a big step up from that old technology. And they did. All aluminum construction, high compression, more efficient cylinder heads, more powerful fuel injection systems. Of course, the Gen 4 engine took that the next step by going to variable valve timing and high gear transmission, the 6L80. And then, of course, the LT took the prize by going to direct injection, really high compression, continuous variable valve timing, cylinder displacement technology, controllable oil pressure, low friction technology, high gear transmissions, 8 and 10 speeds, and I could go on. But here's the deal. What I'm driving right now is putting out a lot of horsepower. Probably more horsepower, in fact I know, more horsepower than an LT1 or a 6.4 Hemi. But how is it making that power? It's not making it through VVT. It's not making it through direct injection. It is making it through somewhat high compression and valve timing. So we have a big cam in this that's putting its power out at high RPM, as we discussed. It has a narrower power band in the high RPMs, but it does put the power out. It sacrifices drivability on the bottom end. We are running a manual transmission. So essentially everything that an LT1 is, this engine isn't. An LT1 is a torque monster. And here's where the LTs get a lot of their power, is on the bottom end. If you guys remember the old 454 Chevys, they even came out with a 502, I think it was. Those things were torque monsters. If you take a 454 LS5, which was a milder version of the LS6, it had more torque on the bottom than the LS6. But when the LS6 hit its power band and the cam came in, it would outrun the LS5. So if you look at pure numbers, that sticker on the air filter, yeah, that's a good indication that which engine has more power. But as far as drivability goes, there's no comparison. Driving this compared to an LT1 is completely a different experience. The LT1 is mild, smooth, tremendous amount of power off the line. In fact, I would say if you race this against an LT1, the LT1 would get it out of the hole, maybe get a car length or two on it, and then once the cam came in on this, it would walk away. But they're both making power in different ways. This is the old-fashioned way, the LT1 is the modern technology. Well, here's the good news for you. To get the power of an engine like this, you don't need to start it and scare small forest creatures away. You can get an LT1, you get an LT6, you get an LT4. And the drivability is just as good as a stocker, if not better. So where does an engine like this come in? Well, it is fun to drive. There's no doubt it's fast, and having a manual transmission for a lot of people is a rite of passage. They just want it. They have to have it. And I will say on the highway, the manual transmission is really nice. You know you're getting better economy because lower friction, even though the new automatics are probably right up there with it, but you're not constantly rowing the shifter. Like I was in Provo in traffic having to go from stoplight to stoplight, and in that situation I'd rather have an automatic. So this video has gone really long. We might do another video on these high horsepower engines. So we're going to take this Jeep to the mountain. We might have another video on this because it's just such a long subject, old technology versus new, but that's where we came from.